Hey everyone, welcome. Today, we are tearing down the walls of C++ inheritance. We've all been there, right? You're staring at compiler errors, completely baffled as to why a subclass just cannot seem to access a parent's variable. Well, get ready because we're going to break down these inheritance rules directly from our source material in a highly structured step-by-step way. By the end of this explainer, you're going to have these concepts absolutely locked in, not just to ace your exams, but for your real-world coding projects too.
Okay, let's dive into this. Here is our roadmap for today. We'll start with inheritance types and accessibility. Then overriding base class functions, constructors, and initialization lists, protected members and access, the infamous multiple inheritance diamond problem, and we'll wrap it all up with key takeaways and exam rules.
All right, kicking things off with Section 1, Inheritance Types and Accessibility. So, understanding how access passes from a parent class to a child class is really the foundation of object-oriented programming in C++. Think of the rules for this almost like a matrix. It's basically your ultimate troubleshooting tool for compiler errors. For instance, if a component is declared as public in the base class, and the class itself is inherited as public, well, the resulting access inside the subclass is just public. It stays exactly the same. Grasping how these combinations resolve is step 1 for fixing pretty much any inheritance error.
To make all of those combinations a bit easier to digest, just remember this simple golden rule of accessibility. Private is less than protected, which is less than public. Private is literally the most restrictive level you can have. You cannot directly access a private member of a base class from outside the class. No way, not even in a derived class. It's totally walled off. Keep this strict hierarchy in mind for all your coding assignments.
Moving right along to Section 2, Overriding Base Class Functions.
Now, you might be wondering, what happens if we need a child class to fundamentally change a parent's behavior? Well, that brings us to a classic exam trap, the difference between overriding and function overloading. To redefine or override a public member function from a base class, the corresponding function in your derived class has to be a perfect match. It needs the exact same name, the exact same number of parameters, and the exact same types of parameters. If that signature changes even slightly, actually, scratch that. It's not overriding at all anymore. It becomes function overloading. Do not let that trick you on test day.
Let's think about how we actually implement this in code. Say we have class A as our base and class B as our derived class, and they both have a print function. Now, what's really interesting here is what happens if a derived class overrides a public function, but you still need to call the original base class version. To pull that off, you have to explicitly call it using the name of the base class, followed by the scope resolution operator, those two colons, and then the function name. So it would look like a.print.
All right, pivoting to Section 3, Constructors and Initialization Lists.
We're diving into the hidden mechanics of inheritance now, because you absolutely have to understand how objects are built and destroyed in memory. This specific sequence is a highly testable edge case. When you initialize an object of a derived class, what happens first? Well, step 1, the base class constructor executes. Step 2, the derived class constructor executes. But when that object is destroyed, the whole process happens in reverse. Step 3 is the derived class destructor executing, followed by step 4, the base class destructor. So the rule of thumb? The base builds first, but the derived destroys first. Keep that sequence locked in.
So that begs the question, how do we actually pass data up to that base class constructor when it has to build first? We use an initialization list. You literally append it right to the constructor of the derived class. For example, you'd write the derived constructor, put a colon, and then explicitly use the base class name to pass arguments up the family tree. It's a direct pipeline to the base constructor. Next up, Section 4, Protected Members and Access. We talked about public and private earlier, but now we're getting into the middle ground of accessibility. The crucial point here is understanding the protected keyword. A protected member's access level is strictly in between public and private. It remains completely hidden from the outside world, like you can't just access it from your main function, but it is directly accessible to derived classes. Basically, it's the specific keyword a base class uses to grant special VIP access privileges exclusively to its own children. Let's rapidly distill how this affects visibility, because this perfectly decodes some of the most dense paragraphs from our source materials. If you use public inheritance, public stays public, protected stays protected.
Simple enough. If you use protected inheritance, both public and protected become protected in the subclass. And if you use private inheritance, public and protected both become private. But here is the major takeaway. Private members of the base class are always hidden from direct access in the derived class, no matter what inheritance type you use.
Okay, Section 5. We're shifting gears to tackle the most complex topic of the explainer, the multiple inheritance diamond problem. Did you know C++ actually allows a single class to inherit from multiple parents simultaneously? It's true. Say class C inherits from both class A and class B. It's a super powerful tool when used right. But what happens when things go horribly wrong in complex class genealogies? Enter the infamous diamond problem. This dilemma pops up when two classes inherit from a common base and then a fourth class inherits from those two. Imagine a base class called person. Then student and teacher both inherit from person. Finally, a teaching assistant class inherits from both student and teacher. The compiler gets completely confused. Without intervention, the system will literally inherit two separate person objects inside the teaching assistant. This kind of genealogy nightmare causes massive maintenance overhead, ambiguous references, and totally redundant duplicate data objects.
Thankfully, there is a built-in C++ fix for this, and it's called virtual base classes. By simply adding the keyword virtual during inheritance, like declaring a class as virtual public, you are telling the compiler to resolve all that ambiguity. The virtual keyword ensures that only the last updated shared copy of the base class data members is actually inherited. It brilliantly and cleanly prevents those duplicate objects from ever forming.
And this brilliantly illustrates a truly fascinating edge case. When you're dealing with parameterized constructors in virtual inheritance, the grandchild class, let's say a copier that inherits from both a scanner and a printer, must explicitly construct the virtual base class itself. Any intermediary constructor calls made by the parents to that virtual base, the compiler literally just ignores them. The rightmost inherited class dictates the data member update. This means the grandchild actually bypasses its parents entirely to initialize the grandparent device directly. How cool is that?
Finally, bringing all these interconnected parts together in Section 6, Takeaways and Exam Rules.
Let's start with a fundamental, theoretical concept that instructors absolutely love to test. What is the precise semantic difference between inheritance and composition? Well, inheritance relates a parent to a child. It is strictly an is-a relationship. For example, a student is a person. Composition, or aggregation, occurs when a class member is literally an object of another class. That is a has a relationship. A car has an engine. Always keep that semantic distinction clear in your mind.
All right, here is your rapid-fire Master C++ inheritance cheat sheet to lock every essential rule into your brain. Overriding, it requires the exact same signature, and you use the scope resolution operator to call the parent. Access, private members are never directly inherited, period. Constructors, the base builds first, but the derived destroys first. And the diamond problem? It is fixed exclusively by using virtual inheritance in C++.
We've covered a tremendous amount of ground today, and I really hope this structured breakdown has empowered you to tackle your next C++ assignment with total confidence. But before we wrap up this explainer, I want to leave you with a provocative thought. Knowing the massive maintenance overhead, the ambiguous references, and the sheer complexity of the diamond problem we just explored, does your future C++ design truly need multiple inheritance? Or could a simple has-a composition save you an absolute headache down the road? Think like a true software architect. Thanks for joining me, and happy coding.